Hello, it's Stat134, Lecture 31. Last time we talked about independent normal variables. So if t is exponential 1/2, we defined r, called a Rayleigh random variable, to be the square root of t, and showed that it has density re to the minus 1/2 r squared for r greater than 0. Using the Rayleigh distribution, we showed that if we have two IID standard normals, that the sum of their squares is equal to t, and hence the sum of squares is exponential 1/2. Also, we showed that the standard normal has constant 1 over the square root of 2 pi, and that the expectation of the standard normal is 0 with SD 1. If z is standard normal, then any normal random variable can be written as x is mu plus sigma z, and we showed that has density 1 over the square root of 2 pi sigma, e to the minus 1/2 x minus mu over sigma quantity squared. And also, finally, we showed, using a rotation matrix, that the sum of two independent standard normals is normal 0, 2. So today we're going to finish section 5.3. We're going to review moment generating functions, show that a linear combination of normal is normal, and introduce the chi-square distribution. As well, we're going to start section 5.4 on the convolution formula for the density of x plus y. So we covered the moment generating function in lecture 25, and recall that the moment generating function of a random variable x is a function of t, and is defined as the expectation of e to the tx for some interval of t containing 0. So common moment generating functions include the standard normal, which is e to the t squared over 2 for all t, and gamma r lambda, where the moment generating function is lambda over lambda minus t to the rth power for t less than lambda. So important properties of the moment generating function is that if x and y are independent, then the moment generating function for x plus y is the product of the moment generating function for x times the moment generating function for y. Furthermore, if two moment generating functions are equal, then their distributions are equal. Technically, that's the moment generating functions have to be equal in an interval containing 0. But in any case, that's a very powerful property. And the moment generating function of a change of scale of x is written e to the bt, the moment generating function of at. So great. So we're going to use these properties to find the moment generating function of a normal random variable. So, for example, if z is standard normal, then any normal random variable with mean mu and variance sigma squared is a change of scale of z, namely x is mu plus sigma z, and the moment generating function of z, as we know, is e to the t squared over 2. So the moment generating function for x is e to the mu t times e to the sigma squared t squared over 2. So that is the moment generating function for normal. Now, then I asked you to use the moment generating function to prove that the sum of two independent standard normals is normal 0, 2. So you took two IID standard normals and you took a product of their moment generating functions, and voila, you see that that can be written as e to the 2 times t squared over 2, where that 2 is sigma squared, and clearly mu is 0 here. So by the uniqueness of moment generating functions, the sum of z1 plus z2 is normal 0, 2. And more generally, if x1 and x2 are normal and independent, then any linear combination of them will be normal with the shown mean and variance. And this is proved at the end of these lecture notes. So then we did a concept test, which threw a lot of you. Let x be standard normal and y be standard normal independent. Find the probability that x is greater than 2y. And so one way to do this is, you know that y is standard normal, so you know that 2y is normal 0, 2, and x minus y is normal 0, 3. So the probability that x is greater than 2y is equal to the probability that x minus 2y is greater than 0. And I'm sorry, this was a misprint here. I meant x minus 2y is normal 0, 3. And so now we're going to normalize both sides of this inequality, subtracting the mean, which is 0, and dividing by the standard deviation, which is root 3. So we get the probability that z is greater than 0, which is 1 minus phi of 0, which is 1/2. So the answer here is A. For the second part of the concept test, you basically have to do the same thing with these two random variables, and the answer was A as well. And you can just read that, it's the same argument. Great. So then we introduced chi-square distribution. So to start us off, if z is standard normal, then z squared is gamma 1/2, 1/2. That's just a standard change of variable formula, and I included that proof at the end of these notes. Recall that if t is gamma r lambda, that the moment generating function is lambda over lambda minus t to the rth power for t less than lambda. Hence, the moment generating function of z squared is 1/2 over 1/2 minus t to the 1/2 for t less than 1/2. So if z1 to zn are IID standard normals, then the moment generating function of the sum of their squares is going to be 1/2 over 1/2 minus t to the 1/2 times n. So we can see that r now is going to be n over 2, and lambda is going to be 1/2. So by the uniqueness, we've shown that the sum of the squares is gamma n over 2 1/2. This is called a chi-square distribution with n degrees of freedom because it's a sum of n independent sum of standard normals. So that finishes chapter 5.3, and now we move on to 5.4, and in particular we're going to talk about the density convolution formula, but we start with the discrete version of that. So let x be uniform 0, 1, 2, 3, 4, 5, 6, and similarly for y. S is the sum of x and y, and we want to find the probability mass function of S. So for example, the probability that S is 3, we can write that as, using the addition rule, probability that x is 0 and y is 3 minus 0, plus probability that x is 1, y equals 3 minus 1, plus probability that x is 2, y 3 minus 2, plus the probability that x is 3, y 3 minus 3. And we can't go further than x is 3 because, for example, if we did 4, then y would be 3 minus 4, but y has to take positive values. So that is not right. So we just are summing from x is 0 to x is s. So I've written here the discrete version of the convolution formula, and now we're going to do the continuous version of this. So we're going to let x and y be positive continuous random variables, s be x plus y. We want to find the density of s. So you can think of s, so if s is x plus y, you can rewrite that as y is s minus x, and think of s as the y-intercept of a line with slope -1. So here's a picture. So the probability that s is in ds, so ds is some interval a little bit greater than s on the y-axis, because it's a y-intercept, and it is the volume above the green region that I have in this picture here under the joint distribution f of x, y. So that is what that's the probability that s is in ds. Okay, now the probability that s is in ds and x is in dx is a little parallelepiped inside of this region. S is in ds. So in here, where we specify x, this probability is again, it's the volume under the joint distribution above this little parallelepiped. So we can write the probability that s is in ds, which is fs ds, as the integral. So the integral, we're summing up all of these dx's as x goes from 0 to s here along the x-axis. Can you imagine this two parallel yellow lines sliding between x is 0 and x is s? So if that's the case, then you'll get all of the probability that s is ds, right? So in the discrete version, it's a sum. We basically sum through all the values of x. In the continuous version, we sum through all the values of x, but there's a continuum of x values between 0 and s. So we integrate instead of add, but it's the same thing. So we're integrating out x. So x goes from 0 to s, probability s in ds, x in dx, and this probability can be written as fx s minus x, which is the height of the joint density above this point x, s minus x in the picture, times the volume, times the area of the parallelepiped in green here, which is dx times ds. So we can write this as integral fx s minus x dx ds, and hence fs is integral from x is 0 to x is s, f x s minus x dx. That's called the convolution formula. That's called the convolution formula for densities. So we ended with an example. So say that x and y are IID exponential lambdas. S is x plus y. So we want to find the density. So of course we know that the sum of two IID exponentials is gamma 2 lambda, but let's just verify that here. So the convolution formula we apply, we using the independence, we break up the density, joint density factors. We write out what we have here. We integrate with respect to x. So that is the integral from 0 to s of lambda squared e to the minus lambda s dx. And notice that the e to the minus lambda x cancels out actually. And so we just get lambda squared e to the minus lambda s times s, which is the variable part of a gamma 2 lambda. So s is gamma 2 lambda as we expect. Fantastic. Have a great weekend, and I'll see you on Monday.